Hey everyone, we got a lot of questions here. I see Leo's here, Cassandra's here, Lily is here, Abigail's here. Thank you so much. Is it Abigail? We started assignment 11 yesterday, so I'll send you that video. We can definitely check that out. We got the sugar questions, so much good stuff. Thank you, everybody. How are people doing today? We're getting started here. How are people doing? Busy day today. Let me make sure Mewbot's awake. Sally, good to see you here. Putting the chat to the live chat. We're gonna get my Pearson loaded up right here. My Pearson loading up. What should we do? We got the sugar question. Sugar. New city. People are saying 3 and 4 on the homework. So we got sugar and new city right now. Man moves to a new city or the sugar question. Leo is saying sugar. A good, who's that? Adam Levine from, why can I not think of Adam Levine's group? Sugar. What is the name of Adam Levine's group? Math classes. Oh, there's a math classes question. What can I think of Adam Levine's group? Maroon 5. There we go. 100 points right there, Leo. Maroon 5. How much sugar? Okay. Chapter 17. People want the sugar question, which is on the homework and the quiz. We're just starting here on some fire. BTS song. We'll just talk K-pop and all different stuff. K-pop, BTS, Maroon 5, Coldplay, Imagine Dragons, all the best bands of all time. So let's get the sugar question going right here. Loading it up in the background. There's the new city. Sugar content. Awesome. Let me take the timestamp. Mewbot's awake. Sugar question starting up. So stat 201, chapter 17, sugar in cereal. Can I spell cereal? There we go. Right there. Here we go. Let's do it. So this is the sugar question right here. And this question is way easier in Jump. I do not suggest doing this question by hand because you will have to go in and solve multiple things. You will have to solve standard deviations and means. The means is the easy part, and you'll have to figure out sample sizes. So what we're going to do right here, have Jump open on your computer and go to this button right here and copy to clipboard. I'll do it in steps, and ask me to slow down if you're watching live, but watch how we do this. We're going to copy to clipboard. Once we copy to clipboard, we get the data. Now notice, yes or no, Y or N in the chat, are there column names right now? Are there column names? Do you see column names? Why? Yes, I see column names. No, I don't see column names. What the heck are column names? It's at the very top where it gives a name to the column. Yup, I see it right there too, Leo. We're going to hit Control Copy. Great job, Bailey, Sally, and Leo right there. Some points in Alexander. So we do see column names. Now we copied it to the clipboard. Then we're going to go over here to Jump. You can be anywhere inside of Jump. If you're on a Mac, it's going to be at the very top of the screen. There'll be a blue bar you have to click on. And on the PC, it's also at the top. Go to File and go to New and then Data Table. 1 second right here. Be right back. Okay, I am back. So we go to File, New, Data Table. With File, New, Data Table, we're going to go and do Edit and then paste with column names. The reason we're pasting with column names is because there are column names. There are column names. So make sure to edit, paste with column names. Now, what color should these columns be when you see them right here? Notice and confirm that you have this, or else the problem won't work properly. What color are they? Confirming this is quantitative data that you've just put into Jump right here. What color are they? Now, confirm you see that. If you don't, restart and make sure to paste with column names. And by restart, I mean open a new sheet completely. If it looks like that, you've done it wrong. So make sure to open a new sheet right there. They should be blue. If they're red, that's a problem. It reads it as categorical because the column name went in the first observation. So we don't want that. We want the column name at the top, paste with column names. So make sure you have this right here. If you've done this, you've done the right steps. Next, we're going to go here and go to Tables and then Stack. With Tables and Stack, we're literally taking both columns and stacking them on top of each other. So we have two columns right here, and they're going to be stacked on top. Tables, stack, double click, double click. So this is going to stack the quantitative information and also take the label of the cereal for us as a categorical variable. Now that we've got both columns stacked, we get a new table right here with the label of the cereal and then the sugar content of the cereal. So we could recall this sugar if you want, or you can just leave it data. It's the quantitative data. When we do a two-sample t-test, the goal of a two-sample t-test is to have two groups we are comparing on a quantitative measure, like children's cereal versus adult cereal, looking at the quantitative measure of sugar. Now, I know this graphic doesn't say this, but literally sugar is quantitative, like how long a battery lasts in minutes. And then we have two groups of children versus adult cereal, and we are analyzing the what between the two means. What are we analyzing in the two-sample t-test? Look at how the t is quantitative, and the two samples is the two categories that we're analyzing. We're analyzing the what between the two means, the difference right there. So we try to throw in a little bit of review here to make sure we understand what this problem is doing. We're asking, is there really a difference between sugar content in kids' cereals and adult cereal? And it's kind of obvious when you think about it. So let's go back over here to our data that we have open in JUMP. So now we're going to go here and go to Analyze Fit Y by X. With Analyze Fit Y by X, we're doing a bivariate understanding of this data, asking does Y in any way be explained by X? Does X explain Y? That's a better way of stating it. Does X explain Y? So does the label of a cereal explain why it has a certain amount of sugar? Like, does the type of cereal explain why there's a certain amount of sugar? We'll go ahead and click OK right here. Oh, it appeared on my other screen. I was like, you can't see that. And here's the data. Now take a look at this. It's pretty much all adult cereal has less sugar than all the children's cereal. Pretty obvious to see. We go right here to the red arrow and we click t-test. This is the two-sample t-test. And with the two-sample t-test right here, we get the following output. Now, if you're in our class, make sure to go over the slides. We put it right here where we've been going through and explaining every bit of this output, making sure we understand how to read it fully. We're going to read what's important for this problem, but you should understand where each of this output comes from, how we would reject the null, and what the constant interval means, and which of these are the tests and the alternatives related to it. So what output do we have right here from JUMP? We have the two-sample t output. How much more sugar does children's cereal have in it than adult cereal? So if you're watching along right now, how much more sugar, read the output right here, did we see in our sample that the children's cereal had than adult cereal? How much more sugar did the children's cereal have than adult cereal on average in the sample? So use the output over there on the side to figure out how much more sugar did the children's cereal have than the adult cereal. On average, the children's cereal had this much more sugar than the adult cereal. On average, the children's cereal in our sample had this much more sugar. Exactly, Sally, great work right there. So this is the estimate of the difference. And see if you can do this. This is something we sometimes ask on the test too. Let's copy paste this output right here. We ask a lot of questions on the test related to this sort of output. Who could figure out, this is a little bit of a tougher question, 500 points in the chat if you get it. Who could figure out the margin of error of this interval? Now, the interval is the answer to the question you're probably working on right now, but we're trying to help out and teach to the test. But you can estimate it. What is the margin of error of this interval? So this value right here is y bar 1 minus y bar 2. If we asked you what the margin of error of this interval is, how could you figure it out? And if you tell me the answer, I can tell you it pretty closely right now. The margin of error, remember, at the center of the interval is the estimate, which is the difference. And then we have a margin of error right here, which is a plus or minus. And we'd have the upper of the interval and the lower of the interval. Leo, good work. Leo, that is the full length of the interval. Leo, good work. So Leo found the full length of the interval going from 30.97, that's the lower limit, to 39.67. Leo, you found exactly, then divided by 2. The margin of error is half the length of the interval. So we're just kind of making sure we understand right here that the difference is the estimate, which is the center of the interval. And then Leo is showing that we would take half the distance. So it's about 4.35. So the margin of error here is about 4.35 higher, 4.35 lower. And you could just do half the distance of the interval. Try solving it for yourself. See if you get the same numbers I did. But the margin of error is half the length of the interval, like 35.32 plus or minus 4.35. And using these numbers right here, we get it. The t statistic right here, which is on the test sometimes, how would we solve this? And then we'll find the answers to our problem right here. Hey, good to see you here, Brent. The first thing that is correct, Brent, that is the first thing on the project is the executive summary. Great answers. 100 points, Brent, right there. How would we solve for this value right here if we didn't have that in our output? Now, remember, when we're doing a statistical test, it's always going to be the difference standardized. So how would we solve for that value over there? Remember, a statistical test, so show me mathematically how we could get this t-statistic right here. What is the mathematics to find the t-statistic, which is the difference standardized? So how could we solve that if that was blanked? We literally did one earlier today that was on the possible test where we had to find the difference standardized. So what is the mathematics to get 16.39 from this output? So that is the t-statistic, which is the difference divided by the standard error. So what is the mathematics? What is the mathematics to get the t right there? What are we doing? So look at I've got some hints up there to show you, and this is practice for the test. Trying to sneak in some test questions. I'm being sneaky and throwing in some test questions while you work on this assignment. So how would you find that t ratio right there, that t statistic, which is the difference standardized? What is the math to get that? Who knows in the chat? I think we said some 500 points. What is the t statistic right there? How do we find that mathematically? Give me another 10 seconds. Does anyone know? So we need the difference divided by the standard error. So the difference is 35.32. The standard error is 2.15. So how about we take the difference right there, that's the difference, which is y bar 1 minus y bar 2. That's what it is. Divide that by the standard error of 2.1552. There we go, right there, another 100 points, Leo. And that is the standard error, or that is the t-statistic, which is the standardized difference. So it's just that. We did one earlier today where we had to solve that in the morning class. So that was on the Canvas content. And so we should have all the answers we need right here. The limits for the interval. I'm going to put it over here on this screen so I can see it, and I'll show you. This is just so I can type it in. 30.98, 2 decimals, to 39.67. And here it is right here. So those are the upper and lower limits. The lower limit and the upper limit, hopefully I've typed them in the right way. Based on this, we are 95% confident that children's cereals average between this much more, I believe, more than adult cereals. So we think the children's cereal has between the lower bound of the interval. And we're going to need our next question. Who's got our next question for us right here? We could do some 320 in a little bit. Definitely. There you go. That is the sugar question, which is way easier with jump, but I would also focus on this question on knowing how to read the jump output, knowing what all this output means. So this question right here is done very quickly inside of jump. You just need to put it inside of jump. It'll solve the interval for you like that. The cities, please. You got it, Alexander. We'll do the cities question here next. That is a solve by hand problem, so a good notation problem question. This one is a good practice on can you understand this jump output, and we tried to go through a lot of it right there. The p-values are over here, and the degrees of freedom, which tell you which t you're using right there. We'll check out the cities problem next. Here we go. Thank you so much, everybody, right here. It is time for the cities problem. You're welcome, Leo. It's a really good problem, especially with practicing. Leo, set us up for success. The cities problem, you know what we need, Leo. What do we need right here for the cities problem? I'll click the button in a moment, the new famous button. Leo, what do we need? I'm taking the timestamps here as we get ready right here for the cities problem. Leo knows what we need. We need, get ready for it, everyone.
Notation, brother.
Notation, brother. Okay. Leo has made their mark on Stat 201 with the notation, brother. Love it. Okay. So this one has a lot of notation. This one wants us to construct a 95% confidence interval. This problem is a bit of a long problem, but it's a lot of notation. We just need to do it in parts. So if you're building a 95% confidence interval for the difference between two means, we have two routes that they can travel, Route B, Route A. So with this, we're trying to ask, is there a difference in how long the routes take? Does that make sense? Like you travel this route to get to work, you travel this route to get to work. Is there a difference in how long the routes take? Like maybe this one takes on average about 12 minutes, or rather, we'll use the numbers. This takes 40 minutes. The other takes 44 minutes on your bike. And that's the average. But is there really a difference, or is that just variation that is just due to, randomness? What is the real difference going on between the routes? Is it just variation, randomness, or is there really a difference where one route is a little longer or a little faster? Now, one thing you immediately want to notice about this problem is in this problem, it is doing the following way of solving it. It is doing B minus A. A lot of times they use reverse alphabetical order. A lot of programs do it that way. So it has to be solved this way. So when I write the equation, which would be on our formula sheet, I'm going to do route B as the first mean. So the equation on your formula sheet is y bar B minus y bar A. It'll have a 1 and a 2, but we're just calling the first route B. Now we go right here and do plus or minus t with the degrees of freedom from the t applet. We would give you that on the test. And because we don't expect you to solve the t degrees of freedom with the 2 sample t is a too complicated formula. We don't solve it by hand. Last but not least, we need the standard error. The standard error of the difference between two means is s1 squared over n1 and plus s sub 2 squared over n2. This is given to you on the formula sheet. Doesn't matter.
It doesn't matter!
Since we're just adding those up, it wouldn't matter if we reverse them. For consistency and notation, I'm going to put B and A on these. B, A, A. If you plus them the different way, not a big deal. Can anyone identify any of the notation in this problem? This problem is tough because there's a lot of notation to identify. Tell me any of the notation. Take a moment right here on the screen. Alexander, Leo, Sally, everyone watching, Brent. Tell me some of the notation. Just see what you can find in this problem. N is 20. I think you're right. Let's look right here. They drive each route 20 days. That means that's this one. They drive that route 20 days. They drive that route 20 days. Good job right there. We've got each route is driven 20 days. So that's they drive route B 20 days. They drive route A 20 days. Each route. So each one has a sample of 20. So that's the sample size for each one. The standard deviation for B. Deviation for B. Yup. That is for B. That's standard deviation for B. Y bar A. There's that. We can use some new colors here. Okay. Standard deviation A is 1. It was time standard deviation. Try to do green for the other route. Cool. Okay, we're one thing short. Oh my gosh, Leo. Ashton, great work, and everyone, good practice. Leo, 1,000 points. Answering it before I can even get to it, Leo. That is some big bonus right there. Leo has suggested we all go over to the applet right here to find the degrees of freedom because you would not solve this by hand. The formula for this, I'll show it on the screen. It's ridiculous. Do not solve it. We had a student saying that they were solving it by hand, and no. You don't want to do it. I'm going to pull it up here so you can see it. It's ridiculous. There we go. So here's the formula right here if you had to solve it by hand. Don't solve this formula by hand. This is why we have an applet. It took about 30 minutes. Oh no. So this, if you want to solve this by hand, have at it. But people told me the standard deviation for route 1 is this is this. They go each route 20 times. So this is, they travel each route 20 times. And since the sample size is equal, it really doesn't matter. I just deleted the rock. Rock no longer matters in this class. But the standard deviation for the first route, the standard deviation for the second route, route A, route B, rock, it doesn't matter because standard deviation sample sizes are the same, so it doesn't matter where you pair them. The degrees of freedom here are 21.36. Now we need to take this and go over to our T applet. The degrees of freedom just tell you the what of your T. The degrees of freedom just tell you the what of the T. As in, here's with 1 degree of freedom, 2. The degrees of freedom just tell you the what of the T. The reason we get degrees of freedom is it just tells you the what of the T. What is changing as I change the degrees of freedom here? The degrees of freedom just tell you the what of the t. That's why we need to know the degrees of freedom. It tells us the what of the t. Always tells us not the center of the spread, I guess the spread to some degree, but it tells us the shape of the t. So now we know it's this t we're using. Like there's infinite t's. Kind of how normal it is. Like you could say the way it looks, it tells you which t, because there's just infinite t's you could use, and each t has its own degree of freedom, telling you you're using a t with this degrees of freedom. So we are using the t with 21.36 degrees of freedom. Preferably, I like to use the between for confidence intervals, and we're going 95%. So I think it said 95%. I think 95% confidence. So there's a good bit of work required to get this t-score. We had to get the degrees of freedom as the first step, and then you have to go to the applet is step 2. So make sure to do this step-by-step process we just did. It's not super quick. You have to go over, find your degrees of freedom, and once you do that, find your t-value. Your t-value probably won't be the same as mine because your degrees of freedom will probably be different than mine. And that is the t-value right here, and it is the step of finding the degrees of freedom via the link Leo put in the chat, and then also going to the t-applet afterwards. So make sure to do that and check those links that Leo put and then I put to get the right t-value. From here, what do we just do? What do I do now? I'll start doing it, and watch as we do this right here. What do we do? What do we do? Oh, thank you again, Leo. What am I doing? Plug in and solve. Oh, is it? This one's the 4. Squared over... way back in time. 4 over 20 squared plus 1 squared over 20. Tell me if I get something wrong. Exactly. You find the degrees of freedom using the degrees of freedom applet, then you put the degrees of freedom into the t-applet. Ashton, great answer right there. That is correct. It's a bit of a long process. It's a bit of work. And it's not as fun for this one. 4 plus or minus 2.08. And that's going to be 17 over square root times 2.08, 1.97, 1.92. There it is. 4 plus or minus 1.92. So it's about 2 to 6. About 2 to 6. Not quite, but we're going to do 4 plus or minus 1.92. Make sure when you solve this to go down here, and this would be 2.02 because that's the minus on it, and then the plus on it is going to be my brain's working, 5.92 because the 4.4 is in the center, and then the margin of error right here is plus or minus 1.92. That's the plus, and then the minus of 1.92, just showing how this is the margin of error right here. And then the center of the interval is your estimate of the difference found from the sample distance difference from the means right here. The sample means had this difference, and then the margin of error right here is everything after the plus or minus, which includes the critical value, the t we are using right here, and the standard error over here, the standard error of the difference. That's just kind of small notation for that being the standard error on the other side of it. And at this point, we've turned it into the margin of error total. That value there has been found to be the margin of error. So this is the final answer, 2.02 to 5.92. And as long as we did the math correctly, we should be good. So 2.02 to 5.0, something doesn't look right. It's not symmetric. There's an error down there. That's why we use calculators. It is not that. It is this. There we go. Error on the screen. Caught it before it happened, though. Watch out. I am capable of making errors, especially if you do something in your head. Someone's saying, wait. So we have 4 minus this, and there it is right there, and 4 plus this. Easy enough to put in the calculator. Double check your work. 2 decimal places. Does the claim of 5 minutes sound believable to you? And this is a good way of doing hypothesis testing. So if someone hypothesized to you that the difference is 5 minutes, would you believe that claim or not believe that claim? If someone hypothesized to you that 5 minutes is the truth, would you say, or would you say, sure, why not? That's possible. What would you say if someone hypothesized to you 5 minutes as the claim? If someone hypothesized to you 5 minutes, what would you say? Yeah, it's in the interval. So, explain. Yes. So, should the man believe the claim that 5 minutes is the true difference? Oh, wait, Jesse. Oh, thank you, Jesse. 500 points. Well, I'm so glad that you're here. Well, awesome. Thank you. Are you in our Stat 201? Are you in Stat 201? Are you like another university? Sometimes we have visitors from other universities. You don't have to say everything about who you are and where you're from, but Jesse, we're glad to have you here. We'll throw you a little randomness. Glad you're here. We always are just super happy. So we can go a limb and make Jesse a mod. We appreciate that. That makes my day right there. That's so glad to hear that we've helped you out. Yes, because the confidence roll contains it. The difference seems plausible. Watch me get it wrong. Wait, let me double check. Yes, because the confidence roll for the difference contains 5 minutes. Okay. Woo! Got a little bit scared, Jesse. I was like, we're gonna get one wrong right now, but we did all the notation on this problem. This problem is a major know your notation problem. We've color coded it here to help out. So start off the problem and follow through. We've got color coding on each thing, making sure we know which thing. Oh, I should have done that the same color. Well, cool, awesome. Well, yeah, glad we're here to help. And good stuff. We went through and did the problem right here. Talked about the center and the margin of error. Well, that's the T. We should color code that differently. Decent color coding, not perfect, because we're not perfect here on Stat 201. We just try. Let's do another question. Who has another question? Drop your questions in the chat. We got a lot of review coming up as we get closer to the final. That's sad music. Let's play Celeste music here. Celeste, great game, climbing up a mountain. We can do some 320 come up here soon. But what questions are there? What questions are there? We've got more questions on chapter 17. You name it, we work it. We explain it. We've got hot dogs. We've got standardized test. Store A, Store B. Let's go check out some Store A. Thank you, Mary Catherine, right there. Store A, Store B. Store A, Store B. Got it up. Got it ready to go. This is a notation one, so we're going to practice our notation again. Store A versus Store B. So, Stat 201, Chapter 17, Store A and B. Okay. Taking the timestamp. Here we go. Let's do it. Remember, drop those questions as we're working away right here. We can work on any question you want. Here we go. So this one is doing a hypothesis test, and it starts by giving us the notation. Now, this one is super nice because it automatically gives us the notation over here for the problem, so we don't have to worry so much about
notation, brother.
A little bit easier. It says first to identify the null and alternative. Now, here's a good review question. Do we look to the data for the alternative or the researcher question? Which of those? How do we figure out the alternative when we're doing nulls and alternatives? Well, the null has the equal sign. That's easy. Dang it, that didn't help us out because all these nulls have equal, so they've done that right. They're investigating the difference between the means, which is the first thing in the interval, or the, excuse me, not the interval. We just did an interval. The first thing on the test is the parameter we're investigating. So they're looking at the difference between two means. They're hypothesizing it's 0. But do we look at the data to figure out the alternative or the researcher's question? Hints for the test. Do we look at the data or the researcher's question? Which thing do we look at to figure out the sign of the alternative? The data or the researcher question? The question. Yeah, Leo, that's right. The researcher question. I thought you were asking like and then you didn't know. That is correct, Leo. The researcher question. We look at the researcher's question, not the data. I know a lot of people are like, oh, of course the data. No, you first come up with a question, then you collect data. So you'd say like, I wonder this. Well, let me go collect data on it. So let's see what they're testing right here. Boop, boop, boop. Do customers spend more on a trip to store A or store B? So they're asking, do they spend more at either store? Okay. Does that sound like a greater than, less than, or not equal to? Now you have to be careful. It does say more, but it's saying, do they spend more at store A or store B? Does that sound like greater than, less than, or not equal to? Because they're asking, do they spend more at store A or store B? So does that sound like greater than, less than, or not equal to? I know it says the word more, which is probably where some confusion might be. Is that a greater than, less than, or not equal to? They're asking, the researcher is asking, do they spend more at store A or B? It is not equals to, because they don't indicate which store they're seeing is higher. They're asking, is it higher for one of those stores? Is it A or B? So it's going to be, it's just asking about a change. Is there a difference between the stores, right? I don't see any sidedness on it. So they're doing a does not equals alternative. The sign of the alternative right here is going to be decided by the way they ask the question. Do they spend more at A or B? Be careful with this more. I could see how someone could think it would be the greater than, but we're not doing that. They spend more at A. It could be B. So is there a difference between what people spend at the store? Now this jumps right into computing the test statistic. So this is where the notation is going to be a huge help. We're just going to take this notation to get the test statistic right here. Jump over here. So now we have to know how to write the equation. And are they doing B minus A? Okay, they do A minus B. You have to know how it's set up right here as A minus B. Make sure to notice it's A minus B. So when we set up our test right here, we need to write the following equation. Y bar A, this is different order from the last one. They've set it up as A minus B. They're trying to trick you. And then we standardize by the standard error. The standard error for this is S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. And this will equal to the difference standardized, which is always going to be a test statistic. The top part of the equation is just the difference between the two sample means, like what is the difference between what people spend at the stores. And then the bottom of the equation is going to be how we standardize that difference, so to give it context and to turn it into a t statistic, which is going to be a standardized difference. Okay, so now that we have this, Ezra, good question right there. What part of the what does this part of the proper? So if you choose the other, like if you chose a less than, choose the greater than test. So whatever for the previous one you just did, Ezra, good questions. If on the one-sided test, Vinaker, good to see you here again. If you chose the greater than test, choose the less than test for the second test time you do a one-sided test. Because like the one-sideds are like the greater than or less than. So it's saying for the next time you do it, the two sample test, choose the, like if you did a greater than on the one sample, do a less than on the two sample. Good questions. Which kind of makes that one a little bit confusing of a problem at times. Or interpretations can get weird. We're just going to plug in our numbers right here. These are the means. The means up here go up the top. Make sure to just do, it says A minus B, do them in that order. Here we'll color code it just in case. This is A. This is B. Those are the means. We'll do some blues for our standard deviations. Oof, that's not going to look good on it. That one will. So standard deviation 1 is for A. So help me get it right. Standard deviation 2 is for B. And then we've got sample sizes. Respective sample sizes, we'll use green for this. So sample size right here for the first. It's still A. I wrote 1s because I'm used to writing that. And then sample size 2 over here. And so just plug in the numbers respectively on how they go, and we should get it right. A little color coding to help out as you're trying to place the numbers and understand how the output works. So we have 44 minus 54. That's going to be a negative difference. The t-score has to be negative. I'll put that right there to start because B was higher. Next, we have right here 20 squared over 85 plus 19 squared over 83, square root of this whole quantity. Be careful, the decimals are going to get rather big on this. Okay, so this is usually where the errors are going to occur on this problem down here on the standard error. 20 squared is 400, divide by 85 is 4.7. We're going to copy that. 19 squared divided by 83, looks pretty good. Add what we just copied, and it's 9, and we're squared, and we're going to get about 3. So the standard error here is 3-ish, which means the t-statistic is about negative 3.32. Because the difference up top is negative 10. So negative 10 divided by 3.334 or something like that. And that's very close to, no, 3.3309. I was thinking of what the t-statistic was. Oh, what are you doing, pen? 09, I'm not blocking it. 009. A lot of fun here doing equations. So I said negative 3.32. Let's check it out. Oh, did I not copy that? I didn't. Okay. Negative 10. That's the difference up top. And the difference of negative 10 divided by 3.009. And there it is right there, negative 3.32. And that is the t-statistic right here that we found. Negative 3.32. Whoo, a lot of work to get that t-statistic. That's a lot of work to get that right there. 3 decimals, and there we go, good. A lot of work to get that. That's a good bit of work. Find the p-value. Now this, we can actually, it wants 3 decimals, probably, and this is the does not equals test. It's probably, I'm doing it in my head right now, probably about this right here. Probably about this right here. Probably. Now, what we have to do to find this is we have to go to first the t degrees of freedom. The t degrees of freedom is where we figure out which t we are using for the 2-sample t-test. So here we are with the t degrees of freedom, and the t degrees of freedom is going to show us which t we are using. We need that output we have right here, and we need to put in our sample sizes of 85 and 83 respectively, and standard deviations of 20 and 19. We compute the degrees of freedom, 165. With 165, it's going to be 0.001. With 165, we now go to the t-applet because we know which t we are using. This just tells us the shape of the t. And here on this, we need to then take and put in the degrees of freedom to show the t we are using. There's the t we are using. Now we know which t we have. We need to do the two-tailed test, which is this, and then we need to enter in our t-score, which is this, and it is 0.001. I shouldn't have guessed 0.002. It's very far off the curve, so I knew it was in the very small decimal region of p-values, 0.001. That's a lot of steps right there. Remember the steps. First, you need to go and calculate your degrees of freedom to tell you which t you are using. The t has all different shapes depending on the degrees of freedom. The degrees of freedom just say, this is the type of t I am using, and it's based on the sample sizes and based on the standard deviations for the 2-sample t to calculate the proper degrees of freedom. Next, once you get your degrees of freedom, go to the t-applet. It's in there in the chat. Put in your degrees of freedom. Once you've put in your degrees of freedom, make sure you've selected the two-tailed test for this one because this is the does not equals alternative. That's the greater than, that's the less than. We're not using those right now. We're using the does not equals two-tailed alternative. And then notice it plots both sides. You can't really see it unless I make the t-value smaller. Then you would see it's plotting both sides of the curve, but we're not seeing that t-statistic. We're seeing this one. The other side of the curve is shaded. It's just very hard to see because it's so small. This is 0.001% of the curve, which is very unlikely, which is where this problem is probably going. So the p-value here is 0.0001. And what would happen right here? Well, using an alpha of 0.10, this is where you can come in and help. Do I reject the null? We need to know this like this. P-value is less than alpha right now. P-value less than alpha, what the null? So P-value is less than alpha. What do you do right here? P-value is less than alpha. You're like, I do this. You just got to be like, boom, P-value less than alpha. Got it. What do we do? This is good practice for the test. I love it if we just like, we instantly know these things. P-value less than alpha. Who's got me in the chat? Who's got it? You're screaming it at home right now. You're like, I got this. I know it, Brian. I'm not live, though. You can't hear me. Surely someone's live. Leo, Vinaker, Priya. Hey, Priya. P-value is lower than alpha. What do we do, Priya? You got it. Leo said reject. If we reject the null, it's because there is evidence for the alternative. So we did some really good marking of this yesterday. We have our statements marked somewhere on here. I think it's right down about here. And take a few more seconds to see if I can find it. Oh, no, it was earlier. When the p-value is low, there it is. So you do not reject the null. You do not have evidence for the alternative. Yeah, that is possible. That means what you saw was super duper unlikely. Technically, p-values of 0 are impossible, but your p-value is very close to 0. So it's just that your t, you probably got like a t of -5, -6, something more extreme than what I got. If you got a more extreme t statistic than I got, like -5, it's just going to report 0 because the probability is so small. It's just super duper unlikely. It's like 0.0000001. Yeah. At that point, you're going to reach the bounds of improbable, like virtually impossible. It doesn't have enough decimals to calculate it. I will say this though. What we could do, Leo, is we could go over here to R, and I was doing some stuff on Fibonacci sequences yesterday just for fun. I get bored. And you could go to the TQT. Is this right? No, we want to go to PT. Degrees of freedom. Wait. Oh, I'm forgetting how to do stuff today. P degrees of freedom. Oh, wait. PT. Q degrees of freedom. Okay. There we go. So negative 3.89. Leo, your actual p-value is the following. This is it right here, and if you took this value and rounded it to 3 decimals, it's 0. So that's your actual p-value right there, Leo, carried out to all the decimals. But because we're rounding to 3 decimals, yeah. So you can find out the actual p-value. It's just so small that it's basically 0. But that is the actual, if your degrees of freedom are the same. Microwave popcorn, you bet. So I just want to point out that we can calculate more exactly, and statistical software will allow for that. The visualization software is just after so many decimals, just say it's 0. But it's not exactly 0 to Leo's question. Good stuff. Did we get that 100? We're going to do Alex's question here next. Check the answer. Got that 100. We've been on a streak. We haven't gotten a question long for like a week. Now that we've said that, let's go do some popcorn question. Leo, we're going to get a question wrong here. It's going to happen because I said it. I should have never said it. I'm going to get nothing right anymore. Nothing. You say, Brian, we don't trust you anything anymore. Is it, I think there's 2 popcorn questions, right? Let's do both popcorn questions. I think there's 2 of them. Stat 201. Chapter 17, popcorn questions. Okay, I think there's 2 of these. Okay, let's go check it out. 4207. Okay, so we have right here is suppose an experiment was done to gather data on the unpopped kernels of microwave popcorn. Half the students in your class took home the bag, put it in the freezer overnight, and popped it the next day. The other half took the bag, left it on the counter, and then popped it the next day. Each group counted the number of unpopped kernels. Yep, we did cereal to start, Priya. Good question. I think it was one of our first ones. I think it was the first one. Check out the start of the video, 5 minutes in or so. Which of the following is an appropriate alternative? Okay, so we can eliminate, and it says, which of the following is appropriate alternative to test whether the freezer method left fewer? So I had less. So when we do it, we don't use the sample mean for the parameter of interest. That's just wrong. You can kind of do one of the classic like eliminating choices and figuring out based on how they did it. This would be that there's not the same amount. And read this. The mean amount left unpopped in the freezer is less than the mean amount unpopped in the counter. So this would be the right one right here because we say which is the following to test whether the freezer method left fewer. So this fewer right here is asking, does the freezer have on average fewer than the counter method? We should get that right there. I think there's another popcorn one. See if there's another popcorn one. I'm pretty sure there's 2. Yeah, here it is. Suppose an experiment was done to gather data on the number of unpopped kernels. Half the students took home the bag, put it on the freezer. Half the bag took it home, left it on the kitchen counter, and popped it the next day. Each group counted the unpopped kernels. Could this method in this chapter be used to compare the 2 means? So what are our 4 conditions for doing the 2-sample t-test? Who can help us out here on condition number 1? Condition 1 for the 2-sample t is what? Condition 1 for the 2-sample t is what? What is our first condition for 2-sample t? Condition 1 for 2-sample t is what? Great job right there, Alexander. Random. Mubot loves some randomness. So we need to sample random. So they want to just pick, they just want to go to a grocery store and pick random popcorn bags. Okay, cool. We got that. Probably they did that. Condition number 2 is they need to sample less than what % of all popcorn bags that exist as popcorn bags. So it's just 10% exactly. So I'd say it's safe to assume that the popcorn bags they're using is less than 10% of all popcorn bags in the world. Like, it sounds ridiculous. Like, why would you need to do that? It goes to the way that finite populations can be sampled. We almost debate not teaching you it because it's rare that you sample more than 10%. It just deals with samplings from small populations. Like if you want to sample UT students, if there's 30,000 UT students, you wouldn't sample more than 3,000 unless you'd break the 10% condition. But for things like sampling like popcorn bags, there's millions upon millions of popcorn bags. You're not sampling more than 10%. Close, Alexander. It's not for the 3rd condition. Now, we always pause when we get to the 3rd condition, and we ask ourselves, what kind of data are we working with? For the 3rd condition, we always say, what kind of data are we working with? And it's kind of large enough N. It's kind of large enough N. Since we're dealing with quantitative data, we'd want it to be nearly normal, which we could check via large enough N. It's kind of. We now call it nearly normal. but you could check it by way of large enough n. So if it's quantitative, and we pause right here because it's quantitative, how many unpopped kernels are there? We could check that via nearly normal. And you could also do nearly normal via large enough n, which is part of the central limit theorem, hints for the test. Chi-squared we haven't talked about, but that's down here, and this is also down here, chi-squared. I've got a color coded for you to see. These are all the conditions that are on the final, kind of a good review. The last condition that we would need to check is that both the groups are independent. So what does independent mean? Independent means is when you have two groups where they would not influence each other. So if you have two groups right here, great job, Alexander. We have the kernels from the counter group, and then we have the kernels from the freezer group, and we're looking at the difference in the unpopped kernels. So would the bags that are left on the counter some way influence the bags that are left in the freezer? I don't think so. They're independent of each other. They're independent. Like you could say, I don't think the bags on the counter are going to influence the bags in the freezer. What a paired test, and this is, we don't do paired tests in this class, but the paired test, which we don't do, but I'm just going to tell you what it is so you know when you wouldn't use the independence condition. A paired test is something like the Biggest Loser, where the first person on the Biggest Loser right here has a before weight of 800 pounds and finishes at 550. Now, they lost 250 pounds, but their end weight, which is the second group of means, like the average end weight of a contestant on The Biggest Loser, would depend on the before weight. Like you would say, well, this contestant started off at 300, therefore for 300 pounds, they wanted to lose some weight, and they went down to 120. They only lost 180. And frankly, they're probably at a pretty decent weight for themselves if they're happy with it. But the end weight of a contestant would depend on the before weight. And you just say, does someone's end weight on The Biggest Loser depend on what they started out weighing on The Biggest Loser? Yes. You just have to think about it. You'd say, with what somebody ends as their weight on The Biggest Loser, like they ended at 100 pounds, would their start weight kind of tell you something about that? Yes. Knowing what someone started with on The Biggest Loser would kind of tell you, information, i.e. their end weight would depend on what they started at. So you would know something. Not for certain, but it's what you end with on The Biggest Loser is going to depend on what you start with. And so this is what we call a paired test. We don't do it in this class, but it's just good to see. So we've gone right here and we've checked all conditions to simply answer, yes, we could do this. Woo! But this is a good check of conditions. We want to know more than just the answer to that is yes. What other questions do we have? We could do some 320. We did some 320 yesterday, but we could do it. What questions are there? Drop those questions in the chat. Remember, you can drop questions anytime in the chat. We haven't been thinking in a while. We're just relaxing with our last sip of coffee. It's gone. Sad times. Last question D on homework 11. Ooh, Alexander wants to do things. We'll do some 320. The coffee's gone. And it's time for 320. And my bind keys to do the zoom in is no longer doing it. We just have... Oh, I thought it wasn't going to go back, Alexander. I thought I had made the screen go gray. And this is last D on homework 11. Great job, Alexander. Oh, the last like D, like 1D? Is it 1D? I think it's 1D, right? The standard test question, if there's time. Yeah, standardized test. You bet, Priya. You got it. Okay, let's see right here. Is there a model predicting... Awesome. Let's check this out. All right, Brian, wake up. Stand up straight. Okay. Let's go check this out. Here we go. Question 1D, assignment 11. Okay, taking the timestamp right here. Thank you, 320. Always feel free to ask questions here. Here we go. And is the model, let's figure out what model we have in a moment here. Any better at predicting clicks than the naive model? Justify your answer by completing the total number of misclassification for this and the naive model. Note you can ignore any warnings saying that a prediction from the rank deficient fit may be misleading. Okay, so with this, we're going to talk about how to look at the naive model. We're trying to figure out, I think, if somebody clicks, right? So I did gender right here as a different model. And we're trying to figure out if somebody clicks. let's take a look at just a model we've created right here and look at our ability to classify someone's gender. And this was asked male, female. So we're going to take a look at the data right here. It's homework 12, right? Oh, it's homework 12. Yeah. 1 second. Homework 12. Alexander, no. We've wasted seconds. Alexander, 100 points. It's my fault, too. Homework 11's already done. I should have realized that. Alexander was seeing if Brown was awake. Little chill music right here as we get assignment 12 going. Assignment 12, I was like, look at some misclassification right there. Getting assignment 12 going. The bonus assignment. Well, kind of bonus. The freebie assignment, but really good to get going on this right here. Assignment 12. Model building. Everybody's having a good time. Here we go. Model building. I probably had it from there. Just called it model building. Okay, let's see right here. 51:45. Let's do this. Here we are with homework 12. Let's look for, is it 1D? There's only a D, right? One. There it is right there. Imagine the goal is to answer, what is the difference between days that rain and days that don't rain? Column weather. Based on the best model fit so far, is there a simple answer, 500 bikes, to this question? Or e.g., is that the difference? Or is the answer more complex? The difference depends on wind speed, specific day, blah, blah, blah. If the answer is more complex, be as specific as possible as to what other quantities must be known for us to be able to compare the difference in average demands. Oh yeah, so let's take a look at this right here. Turn off the music real quick. Okay, so this is the model building portion right here. So let's actually build a model. Okay, so what we're gonna do is, if we have a data set right here of like survey 10, and I want to figure out the GPA of students. This is going to get pretty interesting, Alexander, because how many different models are possible? This kind of goes to the first question here. I have 19 variables, and I'll explain why I have 19. Because there's 20 total variables, but one of them will be used as my what? When I do the reg subsets, one of these variables will be used as my what? I'm going to predict GPA of students. So why do I have 19 X's? Tilde what? I have my Y variable, right? The math test, you bet. We've got the, I think so, standardized. Yeah, we got the, we'll try to do that. Sally and Priya, you got it. So we got one variable as the Y. And then think about this. We have, looks like 16 X's. Let's write this. 16 quantitative X's. One, I mean, it's 7. No, I think 2 categorical 2-level X's. And you see one of them right there, significant other, and the other one right here, gender. And then 1 categorical 3-level X. Okay. So the question becomes, how many X's do I have? How many, does this make sense, Alexander, right here? How many X's? This goes back to the first part of this assignment. So if you're watching this, this also answers how to do the first one about how many different models are possible. First step, and we were doing this yesterday, is to figure out how many X's are there. So each quantitative introduces, so see if you can solve this along with me, each quantitative introduces one possible coefficient estimate. When you have a 2-level categorical X, that would introduce one coefficient estimate. 1 times the 2 is that. Alexander might have figured out the answer. And then we have 2 coefficient estimates from the 3-level, because 3 levels introduces 2 indicators. And sports report, Lily, you got it. I think we might just have enough time to do 2, maybe more set to ones. Great job. Thank you, everyone, for being here. Lily and Sally and Alexander, great work. And Priya, other people too. I think I missed anybody? Great questions. So that is, wait, I said 2 right there. 1. So that's 20, right? Alexander, are you getting this right here? That's right. Nice job, Alexander. So there's a lot of models. So it's going to be a little bit interesting when we run this. And this is what you'd be doing right here to find out the possible models to predict GPA. Let's run this, and let's call this models. This is all possible. No way did. Really? No. Really? Well, let's see what happened. Okay, apparently it did it. Well, I'll be. So the best model right here to predict someone's GPA is their weight, their text, their number of tattoos. Now, Alexander, we're going to do something here that we shouldn't do. It's called a bad idea. The bad idea I'm about to do is the following. I'm including what? What have I just included in my model specification? And I might even have to go cheat and look this up. I can't remember the equation. I never remember this equation off the top of my head. What have I included all interactions. Do you know the equation? It's like 2 raised to the k plus 1 divided by, you use the amount of x's, but it's, if you know it, my eyes, I should never typed. Oh yeah, this is a bad idea. Let's do bad ideas. Oh, it's mad. Oh, I gotta do really big equals true. You have to tell it. It's like, hey, look, you don't want to do this. Really big equals true. Woo! If this actually, we'll give it a 15, 20 seconds right here, but I'm allowing for all possible interactions. And so this is the theme of this problem right now. So I'm basically going to kind of talk through this. You should at this point have a model, right, Alexander? Have you created, I don't even know if this will run, because this is looking through probably, I'm not even joking, over, I dare say, a quadrillion or quintillion models. This is probably looking up towards a quintillion, if not more models. Like, we're in the quintillion model range. Think about how quickly it just did that 1 million plus models. It did 1 million models like that. This is over a quintillion models probably, I would estimate. It's a ridiculous amount. Okay, computer. So with this right here, if I eventually get my models to look at, you would think that they would probably include what's. If we were to get a model, which you should have a model by the methodology you've been using right here, if you did have a model, the models would probably include what's. Just by virtue, we're looking through all these different possible ones here with putting them in our model. The model would probably have what? What do you think the model will probably have in it, Alexander? Because I'm looking through these to see interactions, right? So the question is asking about, is there a simple answer? A simple answer of like whether has this impact would be if there's no what. You'll be saying the same word again, but do it anyways. A simple answer of like the impact of weather is this because there's no what on it. It would just be like, there's the coefficient rain. And that means if it's raining, we expect this impact, or the predicted difference between 2 days where it rains and one where it doesn't is this impact. So if you were to see no interaction, then it would just be a simple answer about the coefficient of rain. But is it more complicated would be, if there's interactions. So what, if you want to look at your model to see if there's possible interactions, what code would you write, Alexander, after you make a model? So if I were to make a model right here, like if I do get my models and I do make them, what code would you look at your coefficients in your model to see if there are interactions at play? So think about that and put that in the chat, because you'd have to look at this to then describe it. So I'm kind of like doing most of this work right here and talking through it, because let me put it this way, there are interactions. So what would let you see the interactions in the model? Like what code would we run to summarize our model? I would do, you could do C interactions, 100 points right there. It's probably gonna do a lot of graphics. C interactions would do it, and I'd probably do summary just to look at the coefficients. C interactions is gonna let you kind of see the interactions and how they work. Summary, both of those are, Alexander, that's another 100 points. Both those answers are correct. I'd probably do the summary, C interaction, and then don't worry about describing it too in depth. Talk about what's interacting on it. Be like, oh, there's a strong interaction here, but there's an interaction with this many variables. Does that make sense, Alexander, how to answer this, to look at the summary and say, there's really strong interactions on this. There's also interactions on 8 different variables. So the idea of how weather is going to explain demand of bikes is actually a complicated relationship, because the impact of weather highly depends on these other variables and is super influenced by these. So we really can't tell you a direct influence of weather because it's highly dependent due to interactions. That's kind of most of the answer. This is a problem with running an exhaustive method. I have literally broken R. Does that make sense, Alexander? Hopefully that answers most of this question right here for you, as we have literally just made R go kaput. So we're going to head back here. Let me know if you have any questions, Alexander. So higher coefficient interactions are if you see any interactions in the p-value is how we can tell significant, right? So low p-value means significant interaction. And the thing is, the coefficient can be deceiving, because maybe something has a small coefficient, but maybe it has a very large scale. So if something like salary has a coefficient of 0.1, salary might be in a scale of hundreds of thousands, but GPA having a coefficient of 0.1 is on a scale of 1 to 4. So GPA, like we're saying, how does that impact somebody's income or like net worth, let's say? And GPA has an impact, a coefficient of 0.1. Well, GPA only ranges from 0 to 4, basically. So that's not going to have a big impact. But salary ranges from 0 to billions of dollars. Yeah, no, good stuff right there. So you don't really look at the coefficient because the scale of the X can highly, something with a small coefficient might be super important. We're going to have to literally force quit R. I have destroyed R. It's using 10% of my CPU. R was eating up 10% of my CPU. Oh my gosh. So I had to I could hear my computer going, and usually this computer doesn't do that. So R was not happy about me trying to make it do all possible models. Well, cool stuff. We're going to head back right to the main screen, do a little more 201. Okay, 201. We've got the standardized tests, and we've got, what should we do next? Standardized tests, or I think there was another one. What should we do, 201? Shout it in the chat. We'll do new questions right here. Thank you, Alexander. Good review of some of the concepts. That also starts the 320 assignment with how many models do we have. Alexander, really good practice on knowing the amount of models using the exhaustive method. If you have a question, someone said the last question on the homework. That was there too. We'll see which one that is. Might be one we've already done, so we're going to try to do new ones here. It's the sugar question. We did the sugar one. So if you're looking for the last on the homework, that's the sugar question, which is earlier in this video. We're going to try to do another new one. We got the standardized test question, which we haven't done. So standardized test is up for possible standardized test. Standardized test it is. 2 people want standardized test, and that's what we're going to do. The standardized math test question. Okay. And then after that, we're going to send an announcement to the class. Say, class is almost time. We've done a lot of these. Is it S class? Peace level. How does the question start? Is it the... Here it is, found it. Okay. Standardized test question. This is a good one. It was this literally near the end of it. Okay. Let's go solve the standardized test question. Here we go. Okay, so this is the standardized test question. And what is the very first thing you do when you see a problem like this? What is the very first thing you do? First, you probably should zoom in on it. But what should you do? What should you do? Any ideas? Anybody in the chat know what we're going to do? A traditional versus not. And thank you so much, Leo, right there, helping out. What is the very first thing? Notation.
Notation, brother.
This one's a little bit weird on the notation because you have a lower and a upper right here. This is the lower limit and the upper limit. Now, if we have a lower and upper limit, how can we figure out the margin of error of an interval? Think about this. Margin of error is, we got to practice how to find it. So here's a practice problem. You ready? Your friend says dinner tonight will cost between $20 to $30. What's their margin of error? So just solve that like this. And Leo's showing the math right there. So your friend says dinner will cost between $20 to $30. What's the margin of error of your friend's interval that they gave you? And just if you know how to do margin of error, just keep repeating how to do it in your head. $20 to $30 has a margin of error of what? And then think about how you solve that when you said, oh, it's this. And there's a common mistake. So I just want to make sure we don't do the common mistakes here when solving for margin of error. $20 to $30 has a margin of error of what? Zach, that's 100 points. That is the common mistake. So the common mistake, Zach, is to do, and so you got some points right there, is to not do half the length of the interval. The whole interval is a length of 10, but a very common error is to do the full length of the interval. So it's plus or minus 5. Does that make sense right there? And Priya is showing all the mathematics. So if we use easier numbers, it's easier to see, and we can see, okay, it's half the length of the interval is the margin of error. The center of the interval will be 25. Sports Pro, Lily will definitely try to do it. Thank you, Lily. We'll do that one next year, Lily. I think we have just enough time. So 25 would be the center of the interval. So if we do this right here for this interval, be careful. Remember, it is negative. So 3.722 minus. Well, the margin of error isn't the mean. The mean would be the average of the two numbers. The margin of error is the plus or minus half the length of the interval. So, no, Zach. Good answers, good questions. You got it. Keep asking questions. Keep thinking through it. You got it. And so, right here, don't worry, my brain's gonna lose it too. Since we're doing minus, we're gonna do plus. Does that make sense? This won't be the mean of the interval. This is half the length. It might, so that won't be the mean. That's not the center of the interval. If you do 20 plus 30 divided by 2, that'll be the center. Does everyone see right here? The 25 would be found by doing the average. So that's the center of the interval right here. The margin of error is half the length. The length is 10. Half the length is 5. So 30 minus 20 is 10. Half of that is 5. So half the length of the interval, the upper minus the lower divided by 2. Doesn't matter which way you subtract them. Rock's gone for today. We'll get them back tomorrow. But half the length of the interval is the margin of error. So 2.922. And if you average them, you get the center of the interval. Does that make sense? If you average them, you would get the center of the interval. So averaging them gets the center. Round to 3 decimals, good stuff. Next, it asks if we had made a 99% confidence. So think about this. 68, 95, 99.7. So they're going from 98 to 99. Would it be larger or smaller? So they're going from 98 to 99. Would that be larger or smaller? So remember, 68, 95, 99.7. That's the way we do them. So if they're going from 98 to 99, would it be larger or smaller? Would that have a larger or smaller margin of error? Larger. And we just remember as we go 68, that's 1 standard deviation, 2 is 95, and 3 is 99.7. Those are z-scores, but t-scores still work off the same theory that going from 98 to 99 would be a larger because the critical value increases. They're talking about the t because the margin of error increases, the critical value increases. A little redundant, but they're just trying to tell you the margin of error is getting larger and the t statistic is getting larger. This is probably the toughest part of the problem right here. If the difference is positive, that means non-traditional is higher. This goes to knowing the jump output, especially where when we marked it for the other one, I think. Here it is. If the difference is positive, it indicates that the first mean was higher. Here we're looking at the difference between juniors' friends and freshmen's friends on Facebook. And the positive difference indicates that in our sample, we saw juniors had more friends. So if it was negative, we would conclude that freshmen had more friends. And the interval right here is possible negative. So their interval kind of shows the same thing. Their interval is positive to start right here and is negative it goes through. So it could be that non-traditional is that much higher, the positive difference. With 98% confidence, students and it's got to be students plural, so make sure you choose one of these. Students in the traditional math class score on average between this much lower. Oh no, careful. Let me double check. Oy. This one's so confusing. It's tough to read sometimes. It's one of these two. We know that for certain because it's not a student. It's the mean students. That's why it's important to choose students because that's on average for students. With 98% confidence in non-traditional math classes on average no. So this is saying the non-traditional score about this much lower. No, because non-traditional score about this much higher. Students, okay. That is, no. With 98% confidence, we were going to get one wrong. Students in non-traditional math classes score on average between... Okay, yeah, that is right. The lower would be the minus for them, or this much higher. Notice how the 3.722 is how much we're expecting for them to score higher, because that is the positive difference associated with the first number right here. That is tricky. Do these results suggest that there is a difference? Why would these results suggest there is not a difference? Think about this. You're saying maybe the non-traditional score this much higher, or maybe the traditional, see how the negatives here and the negatives here, maybe the traditional score this much higher. What is contained in the interval? Which would be like, I don't think there's a difference because that is in the interval. This is a plausible difference. So since this is in the interval, and what are we talking about in the interval? You should see it right there. It's between those numbers. It also says it in the problem. So we think maybe the difference is that. Maybe there is no difference. So what difference is plausible that would say, I don't think there's really a difference here because this seems possible to be the difference, i.e. it's contained in the interval. So do we think there's a difference? What is in the interval to be like, I don't think there's a difference because this is in the interval, which is a possible value. Well, we'll be careful. Yes, 0 is in the interval, but do we think there is a difference? Do these results suggest that students have a significantly different difference between these classes? No, because the interval contains 0, there is insufficient evidence of a difference. Does that make sense? What if my two positives is, if your interval is completely positive, then that would suggest there is a difference. Great question there, Sally. If your interval is completely positive, then you would have evidence of a difference. Does that make sense? If the interval is completely positive, then we don't think 0 is a possibility. Cross your fingers, everyone. Woo! Getting so afraid. We're on a streak right here. Hey, Fran, great to see you. We're going to hop to the main screen. We're going to do, it was Lily's question next. Thank you, Lily. Over here to the main screen. Okay, one moment, everybody. We are sending out, can you explain C with the positives interval? So remember, if it's all positive, then that means that the non-traditional score is between this much to this much higher, because that would be a range of how much higher the non-traditional is. So if it's completely positive, then that would be your estimate for how much higher the non-traditional method is. It's a lot. Interpreting the difference of the two sample T is a little bit much sometimes. We are going to send the announcement to the afternoon class. So one moment right here. Lily will have your question here next. 25 minutes till afternoon class. If I don't send them the announcement, people don't show up. Class in 25 minutes. See you soon. Click here. I should make a bot that sends like an announcement link. Be pretty interesting. Okay, there we go. We got it. Okay. Sally wanted us to work on... Can't wait. Yeah, Zach. Awesome stuff. Sally said sports reporter. Our last question of the day right here. Sports reporter. This is a notation problem. Notation, brother. Scares me. And there we go. Stat 201, chapter 17, sports reporter. Okay, let's go do it. Here we go. Okay, it's the sports reporter question, and it's all about that notation. So make sure you know how to mark every bit. No office hours later, Priya. I might be doing something for 320, but ask those questions, Discord them, email them. We might, never know. I have a meeting later tonight. Ooh. Gonna probably do the, can you cover the math test question? It's super quick. Yeah, I think we can. We'll try to do that super quick, Leo. I think we can speed run it. Okay, so let's help out here. Are you ready, everyone? So what we need for this problem right here is we are going to do a two-sample t-test. For the two-sample t-test, is it bar charts or box plots? Box plots, Ben. Good question, Ben, right there. It would be box plots because it's quantitative. Bar charts are for only categorical data. So you are looking at box plots right there. Bar charts are for categorical. Box plots are for quantitative. So you can do side-by-side box plots. That's when you do the two-sample t-test because you're doing a quantitative y variable up there, quantitative y, and categorical x. Side-by-side box plots would be for two-sample t. Good question, Ben, right there. And that's what we're doing right here. We're doing the two-sample t. So we have two quantitative measures on a baseball versus a football. And we're asking, is there a difference? Suppose, what are they testing? A researcher suggests that professional baseball players must be on average older than football players. Since football is a contact sport. So the way we can write this right here, and which way are they doing their muse? Testing the means. They're saying let the first be baseball. Okay, so we're going to write mu baseball. Mu baseball minus mu football. And what would the null assume? I need help. Whenever we write the null would assume, and they're calling baseball 1 and football 2, so we've got this ordered correctly. What would the null assume? What would the null assume? The null assumes that the difference is equal to what? Well, is what? Is equal to 0. Exactly. Equal sign. Null always has the equal sign. Good practice for remembering the null has the equal sign. Now, the alternative has the sided nature of the question. Great job there, Zach and Fran. Excellent work. So when we do the alternative, we have to ask, what is the researcher asking? They're saying baseball players must be on average older. So they're looking at the average age and wondering from a sample, do we have evidence that baseball players are older on average? Now, if baseball players were older, would this difference between the two means be greater than 0 or less than 0? So this one doesn't say no change. This one wants to know, are baseball players older? That's what they're wondering about. So if baseball players were older and we do baseball minus football, would we get a positive or negative difference? It'd be greater than 0. Does that make sense? Because think about like baseball would be older, so we'd see a greater than 0 difference. So we're saying, and you can, one trick for this is to just plug it in right here between the two numbers. What do I mean by that? If you just plug it in, you could write it this way. It doesn't keep to the same format, but you could just say baseball greater than football, and you've still put it in the correct way. It's just because this could mathematically go over here, but it's still the same algebra. Does that make sense? It doesn't look the same formulaically, but you can just plug it in right there. But that's a trick to make sure you have it correct, to just read it off like baseball greater than football. Just remember the greater than would just go instead of the minus, just the way algebra works, because that's literally just going to that side right there. So that's just a trick to make sure you write it correctly and can read it. Okay, now that we've found the proper alternative, we have brought here this one. There we go. Now it wants the test statistic. The test statistic is going to be computed by solving the
notation, brother.
Okay. So let's go ahead and mark our notation. I might not color code everything because we got one more question of this. So we're going to do it a little bit quickly here. So the notation for this is y baseball minus y football, y bar specifically, over s sub baseball squared over n sub baseball plus s sub football squared over n sub football. Those are the sample sizes and standard deviations respectively. I'm going to disappear right here. And so baseball had an average age of 27.48. Football had an average age of 26.6. The bottom, which is the standard error respectively, is 4.03. We've got to square that over 33 sample size plus 2.68 squared. Remember to square it. I sometimes forget. Over 34. That's going to be the standard error. Let's solve for the standard error and then divide the difference by it. So the standard error, which is the bottom of the equation, 4.03 squared divided by 33. We're going to copy that because we're going to need it. So if you don't copy it, make sure to write that down. That is the value we just found there. It's about 0.5. Don't round it. Don't round it. Don't round it, because then you'll get errors. We're copying it. 2.68 squared minus 34. Don't round it. Add it to the previous value and square root it. So there we go right there is the value of the standard error. Double check your work. That's where your errors are going to happen. This is already square rooted. So that is the value of the standard error, which is what we're going to divide the difference by. I'm going to copy this right now because I'm going to find the difference, then divide it by the standard error. So 27.48 minus 26.6 divided by the standard error. We've just found the t-statistic of 1.049. Now, this is a really cool t-statistic because I can take a guess at the p-value, 1.049. That is the t. What is the formula on the left again? This is the two-sample t-test, the two-sample t-test. We have two samples, and we're standardizing the difference. Great question right there, Zach. That is the two-sample t-test, two-sample t-test. And so now we have to go where? Leo, where are we going to go? Because we need to take this, and where are we going to go? We can take a decent guess at what it is. Where are we going to go? We need to figure out something else for this. So that's what we're going to do, and this is what we're going to find. It's going to be close to, if I had to guess this p-value, the p-value is going to be close to about 15%. Yep. Oh, remember, we're going to get the degrees of freedom. And so MuBot can help out with the TDF right there, the T degrees of freedom. We have to know which degrees of freedom we're doing. So here are the degrees of freedom. Applet to find out which T we are using. Take your sample sizes, 33 and 34 respectively. Take your standard deviations, 4.03, and 2.68 respectively. And this tells you which T you are using, 55.45 degrees of freedom. And then next we have to go to the T applet to put it in and find the T score. So to find the p-value rather. So now we're going to go over here and go to the T applet, and you'll see a picture very similar to what I drew. So we're going to go over here and get a very similar picture to what Brian drew right there. We're going to put the degrees of freedom in here. I'm going to zoom in so you can see it real quick. We're going to put the degrees of freedom in. Then we're going to put in the t-score I found of 1 point this and do a right-tailed test. And wow, we got super close. So I said about 15%, and the actual p-value is 14.9%. This is very close to a z-score of 1, but z's and t's are different. So I was guessing about a little less than 16, so I was using the empirical rule to take a guess at it. That was a guess, and this is what the applet finds. But there's a lot of work to get the t-score and to get the p-value from this. So remember the t-score right here, round to 2 decimals. The p-value right here to 3 decimals. And state my conclusion. Now, this part right here, the p-value is high. So since the p-value is high, what do? It's above alpha. Do we reject or fail to reject the null? My p-value is high, just let the null what? So my p-value here is high. So what do I do to the null? Just let it fly. So we're only between answers A, B, C, or D right now. So we're only between answers A, B, C, or D. Look at, before I go to the other screen right here. We'd only be between... Okay, thanks to those people. Oh my gosh, I should mark my documents. That'd be an amazing idea. C and D. I'm trying to find the document for you to see where we talk about rejecting versus not rejecting. We've got it highlighted with the proper text. It's got to be right here. Come on. There's one. Here it is. So you say, I do not reject the null, which is fail to reject. I do not have evidence for the alternative. We're on that one right here. Or I reject the null. I have evidence. I know, right? So we fail to reject the null. There is not evidence for the alternative. Woo! I'm getting scared. Okay, we got one more question here. We did that one a little bit quickly. So review how to do the notation, review how to solve it, realize that we are finding the t-statistic, finding the p-value. The hardest part usually is using the degrees of freedom applet to get the degrees of freedom. A lot of people skip that step right there. If we reject them, we have evidence. That is correct. So if you reject the null, there's evidence for the alternative. If you do not reject the null, there is not evidence for the alternative, i.e. fail to reject or fail. We should say I fail to reject the null. I fail to find evidence for the alternative. You could say that. That'd be fine. Just realize that not reject is not evidence for the alternative because you still believe the null. And then reject the null is evidence for the alternative because you don't believe the null anymore. You believe something different. So we did not reject the null right here. We did not have evidence for the alternative, which is the conclusion of our test. Last question. Leo was asking about, the question was, can you cover the math test question? The math test question, let's find it, Leo. The math test question. The math, how's it start out, Leo? The math, oh, I think I know what you're talking about. It's the students in a summer class, right? Yeah, here we go. Okay, cool. This is a good one right here. Super quick question, then we'll be done. We've done most of it. I think we only didn't do the glass question. Let's go check it out. It is a little confusing. Let's go check it out here. So this is the math test question. And so let's think about what we have right here. We have students are taking a test in June and students are taking a test in August. Who here feels like maybe they're really good at stats? Or let's say it's a class. Do you have a class you're really good at, Leo? Do you have a class where you're like, I am just a rock star at chemistry or biology or English? Not me. English is not me English. I'm more of a math person. Because this is the same student. So if you look at this, it'd be right here. Accounting probability, underwater basket weaving. I was great at that class too right there, Zach. I agree, 100 points. So you have student 1 who takes it in June, then retakes it in August. Student 2 takes it in June, takes it in August. Student 3. So would you say how the student does in August might what? And I wish they made the data a little more obvious on this. How the student does in August might what on June? So think if this is you and you're retaking a test, because we have two means right here. We have the mean for June and we have the mean for August. So we have 6 students right here, and we want to look to see if there's a difference between the means. But how a student does in August might what on June? it would depend. And we talk about this in class today. It's just like and we have this ready to go right here. This is what is called a paired t-test. We don't cover this, but in this instance, this does not meet the condition of independence right here, where one mean would be independent of the other. We talked about a soil example today in class, but here with the paired t-test, you would have that, someone's start weight at the start of the Biggest Loser would depend, or their end weight rather, we would say depend on their start weight. Like someone's August score depends on their July score. Like people who did better in July would probably do better in August. People who do worse in July would probably do worse in August. So in this instance, this is not something we would do right here. These are before and after scores for the same individual, not independent samples. This violates the independent assumption group right there. Yeah, exactly. So you would say like we have two groups. Do they influence each other? Like in some logical way? And think about the other questions we did. Do you think the age of football players influences the age of baseball players? Like, oh, if football players are older, then baseball players have to be older. They might say, well, aren't athletes' ages going to influence athlete ages? Well, that's just in general. But in this instance, the age of football players and the age of baseball players are not going to influence each other in a significant way. They're independent of each other. Other examples we did today were things like store A, store B. These are two random stores. You could say, what if they're in the same town and people love another store more? Well, we're just saying, would the amount things sell for in store A influence the way things are sold in store B? And I guess, I don't know, someone could come up with an interesting way to say there's some dependency, but I don't think so. Do the bags on the counter influence the bags that were in the freezer? No. A lot of times we're looking for a before and after idea, which this question really gets to, is the idea of this is students who take it in June, then take it in August, and there's some dependency here. Well, with that, Leo, great question. You said it. It was a quick one. Until then, we're going to be starting here in 10 minutes. 10 minutes till class. Chapter 17 today. We won't do a preview of Chapter 19, but got a lot to do. See you soon, everyone. Bye for now. Bye. Chapter 17 soon.